Yeah, at this point we've seen a couple different approaches to finding factors of numbers. There's one approach, the Q-sieve, is just a special case of the number field sieve, and not a particularly well optimized special case. It's one of the worst possible cases of the number field sieve. That's trying to find factors of numbers by writing down random squares, combining congruences to form squares that, well, when you multiply congruences mod n, you also get congruences mod n. If you multiply them to form squares, you suddenly have congruent squares mod n, which gives you, hopefully, a non-trivial factor of n. The other approach that we saw is writing down big numbers mod n that are products of lots of primes. And that approach in the form of the elliptic curve method is actually faster than the Q-sieve, but it's not as fast as the number field sieve. The time for the number field sieve, all of these are sub-exponential. The details of exactly what the sub-exponential is tells you how fast these methods are, at least asymptotically. The Q-sieve we saw takes about e to the square root of 2 log n log log n bit operations to factor n. The elliptic curve method takes about e to the square root of 1 log n bit operations to factor n, assuming the worst case for the elliptic curve method, that n has just a couple of large prime factors. The quadratic sieve is similar kind of performance to the elliptic curve method, e to the square root of 1 log n log log n. The number field sieve is considerably better. Instead of e to the square root log n, it's e to the cube root log n for the time taken. Well, it's not quite that good. Let me say that L is e to the cube root of log n times the cube root of the square of log log n, all in the exponent. The time for the number field sieve isn't L, it's L to the 1.9, roughly. L to the 1.9 plus little o of 1. The 1.9 is a certain algebraic integer, maybe 1/3 of the cube root of 92 plus 26 root 13, but don't quote me on that. It's some number you can write down, and that's the speed of the number field sieve. Because of the 1.9, you don't immediately see the cube root taking over instead of the square root. The square root might be better because it doesn't have 1.9, but as n gets bigger, the number field sieve becomes asymptotically much faster than anything we know how to do with the elliptic curve method or, say, the quadratic sieve. Let me once again recap the Q-sieve, and then I will give you a fancier example of the number field sieve. We are once again trying to solve the Diophantine equation, x times y equals 611, which the Q-sieve does by combining congruences, for instance, 14 congruent to 625 mod 611, and 64 congruent to 675, 75 congruent to 686. Multiplying all those together, you form square congruent squares. Taking the difference between the square roots and the greatest common divisor with 611, you obtain a factor, a non-trivial factor of 611. I've stuck in a j there, by the way. Instead of I plus 611, I've written down I plus 611j. It's kind of silly for that particular I plus 611j to take j to be anything other than 1 or maybe minus 1. But in the context of the number field sieve, the coefficient of j, I think the microphone is off. I don't know if people can still hear me. Let's try microphone number 2. Uh-oh.
Here's a jar. Is it jar?
Good morning. Okay, so I was saying in the number field sieve, the coefficient of j is a lot smaller, so it's worth sticking in a j. An example of the number field sieve is the Q-adjoint square root of 14 sieve for factoring 611, which instead of writing down I times I plus 611j and trying to multiply those over a bunch of pairs I comma j to form a square, I'm going to write down I plus 25j times I plus square root of 14j. And in particular, for I equals minus 11 and j equals 3, I wrote down the product minus 11 plus 25 times 3 times minus 11 plus square root of 14 times 3. And then for the pair I equals 3, j equals 1, I wrote down the product 3 plus 25 times 3 plus root 14. Multiplying together those two congruences mod 25 minus root 14, which is really what the Q-adjoint root 14 sieve is factoring here. writing down those congruences and multiplying them, I found a square in Q adjoint root 14, namely the product of both of those congruences is 112 minus 16 root 14 squared. If I then take square roots, well, I know the square root of this number is 112 minus 16 root 14. I also know it's congruent to, the square is congruent to the square of minus 11 plus 3 times 25 times 3 plus 25. If I change the square root of 14s into 25s, then I get a square on the left. Calling s the square root of the number on the left, minus 11 plus 3 times 25 times 3 plus 25, and calling t the square root of the number on the right, and then change square root of 14 to 25. So the difference here is whether you change square root of 14 to 25 first, and then take the square root, or the other way around. Then the difference between s and t happens to have a factor in common with 611, namely 13. It's not unreasonable to imagine that this procedure would have worked, just as the Q-sieve is something that works. If you look at z adjoint root 14, it has a map to z mod n that takes root 14 to 25. Root 14, I see a question. Yeah?
I don't understand what just happened.
You don't understand what just happened. Well, you mean you don't understand what was being computed or why it was working?
Why it was working.
Well, okay, so that's what I'm aiming to say here, is that there is a map from z adjoint root 14, z adjoint x mod x squared minus 14 to z mod n that takes x to 25, takes root 14. N is 611, yeah. Yeah, so we're trying to factor 611, and you will observe that 25 squared is 14 mod 611, because 25 squared minus 14 equals 611. That's how I came up with the 14, was I took 25 and subtracted 611, and I got a 14. So everybody believe we have a ring morphism? Okay, good. So now applying that map to the square, the question of how I found this square, let me ignore that. But assuming that you can find a product of these numbers in Q adjoint root 14 that forms a square, then let me just take that equation, that 112 minus 16 root 14 squared is the product of those congruences, and apply the map to it. In other words, change the root 14s to 25s. And what do I get? I get the equation mod n that minus 11 plus 3 times 25 times minus 11 plus 3 times 25 times 3 plus 25 times 3 plus 25 is the square of 112 minus 16 times 25. And now I have two congruent squares in Z mod n, and I compute the difference of their square roots, take the GCD with n. All right, if you believe that S and T are sufficiently random, constructed by this procedure, then it's not a surprise that the difference between S and T has one factor in common with n, and S plus T has the other factor in common with n, yeah, again, n being 611. The important point is that we do have squares that are the same mod n. Again, what the Q adjoint root 14 sieve is actually forming is squares that are the same mod root 14 minus 25, but, well, root 14 is congruent to 25, mod the difference, and factoring the difference is tantamount to factoring n. Does that answer the question? Okay, good. All right, in general, maybe not in complete generality, but in sufficient generality for the best parameters we know how to choose. In general, instead of square root of 14, we have any algebraic number, which I'm going to be calling alpha. The polynomial that has alpha as a root is, say, f, instead of x squared minus 14. F has to be irreducible. Well, actually, it doesn't have to be, but we don't know how to do better with reducibles. Also, you might think that really we have two polynomials here. There's x squared minus 14 and there's x minus 25, and the product of those doesn't have to be reducible as it is here, but we don't know how to do better with that. So, okay, for me, the number field sieve parameters are there's f, an irreducible polynomial over z, and there's an integer m, which is a root of f modulo n. For instance, taking 611 and writing that in base 25, it was 25 squared, well, allowing negative digits, 25 squared minus 14. I've written 611 as a polynomial in 25, and in general, you can write a number n as a polynomial f in whatever small base m you want. It's easy to write down an f and an m, and usually f is irreducible. Let's in general say that the degree of f is d, and I've given names to the coefficients of f, In particular, the leading coefficient of f does not have to be 1. You can, if you like, rescale, and at the bottom of the slide I do rescale f to form a monic polynomial g, but for parameter selection it's better to think about the coefficients of f and not to insist that f sub d be particularly small. Fd and Fd minus 1 and so on through f0, we're going to see next time, are all allowed to be on the same scale as m. Alpha, as I said, is a root of this. Alpha is like square root of 14. And if f sub d is not 1, then alpha is not necessarily an integer, but you can multiply it by fd to get an algebraic integer root of this monic polynomial g, which I'm just twisting f to make the leading coefficient 1 and make fd. Oops, when I say cd, that is a typo for fd. My apologies. I will fix that online, but not right now. That's what I get for changing notation at the last minute. Okay, in general, what does the number field sieve do to form congruent squares mod n? Well, really mod alpha minus m. Well, it writes down the congruence is I minus jm is congruent to I minus j alpha, mod alpha minus m. I and j, well, what I've written down there is that I and j are co-prime, GCD is 1, and j is positive. If you allowed negative j, it would be just the same as negating j and negating I. There's no point in that. If you allow I and j to have a factor in common, you might as well consider that factor separately, and it's generally useless. In general, instead of I minus j alpha, you could consider higher degree functions of alpha and then corresponding functions of m. But I minus j alpha is particularly small. I minus j alpha as a general element of the number field is surprisingly small for the general element of the general number field. We're going to see more about the parameter selection next time, but something that you can see from even crude optimization of the number field sieve is that I minus j alpha is small. It has small norm. It's smaller than you expect a number field element to be. And if you allow higher degree polynomials in alpha, you lose that property. Maybe quadratics are useful, but it's certainly not something that affects the exponent in the time of the number field sieve. All right, so let's just take linear polynomials in alpha, I minus j alpha, where I and j are co-prime, j is positive, and now form a square in Q join alpha. Then we can use that to factor n, basically by taking the square root, taking it mod n. Well, there's denominators, and let me be careful about the FD. That's a topic on the next slide. To step back for a moment and say the big picture here, there's a few levels of understanding the number field sieve. The first part, which I'm in the middle of, is just seeing the algebra and saying what is it that we're doing to form congruent squares mod n, how do we build those squares, how do we get around little obstruction group that you might call a T-Selmer group. The second level of understanding the number field sieve is seeing that L to the 1.9 plus little o of 1 that I mentioned for the time, the number of bit operations when you choose your parameters in a reasonable way. Both of those I'm going to do in this talk, and the next time I'm going to talk about the detailed optimization, how you really choose all of these, how you choose the range of I and j, how you choose the polynomial f. There's a lot of research problems here which people don't know answers to. People have sort of good answers, but there's clearly room for improvement. For now, I just want to do, okay, suppose you have formed a square, then what do you do with it to factor n? What's the algebra in building a couple of congruent squares mod n? Well, again, you basically take the square root of q join alpha, take it mod n, but oops, there's potentially denominators. Let's clear denominators. Alpha has in particular a denominator of fd, and multiplying by a big power of fd, maybe multiplying each factor I minus jm times I minus j alpha times fd squared. That's probably overkill. Just one fd is enough. As long as you have the total number of fd's being even, then you still have the square, and it's now an algebraic integer. This square that I've written down, assuming that we have product of I minus jm, I minus j alpha being a square in q join alpha, then this new square with the fd squareds in there is an algebraic integer and a square. Now, just because it's in the ring of integers, just because it's square root is in the ring of integers, doesn't mean that the square root is in z adjoin fd alpha for us to be able to take it mod fd alpha minus fd m. But you can easily get rid of that difference, deal with the index by just multiplying by the square of the different, multiply the square that I've written down by the square of the different, multiply the product of I minus jm, I minus j alpha times fd squared by the square of the derivative of g. G, recall, was the polynomial that had FD alpha as a root. If you multiply the square by that, then you multiply the square root by G prime of FD alpha, which guarantees the square root is now in Z adjoint FD alpha. And now, having an element of Z adjoint FD alpha, you can take it modulo, well, if we didn't have a denominator, take it modulo alpha minus m. Since we do have denominators, take it modulo FD alpha minus FDM. There is a ring morphism from this number ring, Z adjoint FD alpha, to Z mod n, that takes FD alpha to FDM. Since FDM is the root of the same polynomial, modulo n. So, applying that ring morphism to the equation r squared equals blah, 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 you get down at the bottom here, phi of r, the image of r inside Z mod n, squared is the square of G prime, applied to FDM instead of FD alpha, times the product of I minus Jm and I minus J alpha, both turn into I minus Jm, with the same FD squared clearing the denominator. So taking square roots there, we now have two congruent squares modulo n. Take square roots of both sides. Square root of phi of r squared is phi of r. Square root of the right side is given to you as, in a different way, as G prime of FDM times the product of I minus Jm FD. And hopefully the difference between those has a factor in common with n, non-trivial. All right, there's some amount of computation to do here, even if you've figured out a set of pairs ij that forms a square as the product of I minus j and I minus j alpha forming a square in Q adjoint alpha. You still have to do some, what did I write down here, some computation of a product of I minus jm, I minus j alpha, fd squared, and then a little multiplication by g prime squared, and then compute a square root. But all that, compared to the rest of the number field sieve, takes negligible time. So as long as you know how to multiply with product tree and take square roots with Newton's method, then all those computations are easy. All right, how do we form a square as a product of a bunch of numbers? Now, how I said, well, suppose we do have a square, but how do you actually figure out your squares? Well, first you form virtual squares, and then you deal with the difference between virtual squares and actual squares. Let's start by saying, all right, we're not going to be able to form a square unless we have smooth numbers. As usual, if I minus jm, I minus j alpha, whatever form you write down, if that has a large prime in it, then probably you're never going to see that prime again, so it's not going to be useful. Let's start by looking for y smooth congruences out of y squared potentially smooth congruences, the usual ratio. So write down y squared pairs I comma j. Just take, for instance, all i's up to y, all j's up to y. Later, you're going to have to throw away the ones that are not co-prime, but that's only a constant fraction of them. Look for I minus jm being smooth. Look for I minus j alpha being smooth, which I've written here to precisely say what I mean by I minus j alpha being smooth. I'll declare that to be that the norm of I minus j alpha with an FD to clear, well, sort of clear denominators, that integer polynomial in I and j is y smooth. In other words, j to the e times f of I over j. That's y smooth. Once you have enough y smooth congruences, then you write down appropriate exponent vectors, which I'll go through carefully. Modulo 2, do linear algebra on those vectors modulo 2. And once you find a subset of your smooth congruences where the exponent vectors add up to 0, then you will have, as a product of the corresponding I minus j alphas and as a product of the corresponding I minus j m's, a square. I'm actually going to get not just the product of I minus j m and times the product of I minus j alpha being a square, but each one of those separately, which is not exactly the same thing, but certainly good enough. All right, what are the exponent vectors? How do you, looking at an element of Q adjoint alpha given in this form, the product of I minus j alphas, and then product of I minus j m's, how do you recognize whether one of those products is a square? Assuming they're y smooth, you just have to think about primes up to y, but what do you do with those primes? Well, the easy part of that is making I minus jm have square product. Again, I'm going to make both I minus jm have square product and I minus j alpha have square product. Slightly overkill, but okay. for I minus jm to have square product, well, each exponent vector has some rational components to it, some rational primes less than or equal to y. Just write down the power to which those divide I minus jm. For each prime p less than or equal to y, write down order sub p of I minus jm, mod 2, and that's the p component, p rational component of your exponent vector for the pair I comma j. For minus 1, for dealing with the possible sign of I minus jm, write down the log base minus 1 of the sign of I minus jm as another component. Then these components of the vector are going to add up to 0 if and only if the product of I minus jm is a square. All right, that's the easy part, just like what we were doing, well, with the addition of the minus 1 in here, just like what we were doing with the Q sieve. To recognize squares, just write down products of exponents of primes in factorization. For the algebraic side, for I minus j alpha, you do the same thing. And I guess the important part here is not that there are factorizations, but that they're so easy to compute. You don't have to do any algebraic number theory computations to figure out the exponent vectors for Q adjoint alpha. For every prime p less than or equal to y, you get a first degree prime over p for each root of f modulo p, assuming I'm going to stay away from some bad primes. I'm going to stay away from primes p that divide fd. I don't want f to drop in degree. I'm going to stay away from the discriminant, maybe overkill, but there's not too many primes dividing the discriminant. And now for each root, for each r, that's a root of f in fp, to s, a root of the polynomial f in the field z mod p, you get a first degree prime of the ring of integers of Q adjoint alpha, generated by, well, p and fd alpha minus fdr, or ignoring the denominator there, basically alpha minus r. All right, at that prime, how often does the prime p comma alpha minus r, ignoring the denominator, how often does that prime divide I minus j alpha? Well, it is a fact which you have to look at for a moment. It's not a complete triviality. It is a fact that that is the power of p in the norm form f to the d, j to the d f of I over j, if I is common to jr mod p, otherwise just 0. What's going on there is that there are no second degree or higher degree primes in I minus j alpha because I and j are co-prime. This would not be true if I allowed I and j to have a factor in common, in particular p in common. Then there could certainly be some second degree primes spoiling the power of p in the norm form j to the d f of I over j. But since I and j were chosen to be co-prime, this is easy to prove. And now you just, once you've written down the integer, j to the d f of I over j, just evaluate the homogeneous f polynomial at I comma j, then calculating the power of p in there, that's the same as the power of this prime of Q adjoint alpha in I minus j alpha. So far, I've just recognized virtual squares, T virtual squares, where T is the set of primes at FD and discriminant of F. But, well, that might not be the same as squares. As you heard last talk, there's an obstruction group there. So, okay, there's more components to the exponent vectors, just a few more components, just enough to deal with this obstruction group. These are called character components, where you choose some quadratic characters you take for some primes different from the ones that I just wrote down, for some primes that don't divide the I minus j alphas, figure out whether I minus j alpha is a square at those primes. I've expressed it here in terms of just integer computations for pairs p comma r, same kind of p's, but now bigger than y, so they don't divide I minus j r, or j to the df of I over j. You figure out I minus j alpha, is that a square at the prime of O? In other words, is I minus jr a square in fp? If it is, then write down a 0 as that component of an exponent vector, otherwise write down a 1. All right, now it is a fact that if you have a square, then all of the exponent vector components that I've written down do add up to 0 mod 2. For the characters, well, if you have a square, then it's a square in FP. And for the algebraic components, well, I said we're doing evaluations, so certainly a square will give you 0 mod 2. What about the converse? Well, question here in a nutshell is, do we have enough characters to deal with the Sommer group? We know certainly the rational components, there's nothing to figure out. If you have a set of pairs I comma j, to make sure the question is clear here, you have a set of pairs I comma j for which the vectors that I just wrote down in detail add up to 0 modulo 2, then is it true that I minus jm has square product and I minus j alpha has square product? The answer for I minus jm is certainly yes, because I've dealt with all the primes of z, minus 1. The answer for I minus j alpha, well, there's the obstructions that you heard about. In fact, okay, so this is very convenient to be able to use the previous talk. So there's unit group obstruction and a class group obstruction, and not reflected in the sequence, there's a bad primes obstruction. So if you have I minus j alpha, the ideal that that generates, then certainly it's I minus j alpha, its product is a virtual square. It's a square outside, as an ideal, outside some bad primes, outside the primes dividing the leading coefficient fd and the primes dividing the discriminant. But, well, there's some bad primes, and it might not be square root those. Even if it is a square root those, then, well, the square root, we might have a non-trivial class group, and that square root might not be principal. And even if it is principal, then the square of the generator of the square root of the ideal might not have, did I say that right? The square of the generator of the square root, that might not be our desired generator, the product of the I minus j alpha, desired generator of the square ideal. The last thing I think is stuck in the name that everybody in his rank mod should be using. This is the FT discriminant of FT delta Sommer group. So this obstruction group, if you actually compute it in small examples, it's small. If you compute it in bigger and bigger examples, it's small. There are bounds saying how big the class group and the unit group are, and the bad primes obstruction, and everything seems small. Conjecturally, it's even a lot smaller than what we can prove. So this obstruction group is really tiny compared to Y. You don't actually want to do this computation. When you're doing the number field sieve, you don't want to do, well, okay, you heard that computing class groups and unit groups takes microseconds, but if you scale up to the sizes of number fields used in the number field sieve, it might take perhaps more microseconds than you want to spend. But that's okay. You don't need to know how big this group is. You just write down, say, 50 characters. That's overkill. I haven't heard of anybody doing number field sieve computation and needing even that many characters. You write down 50 character columns in these vectors, and each character defines a seemingly random element of the dual of this group, and once you have enough characters to generate the dual, then, okay, you've killed the group. You know that the product of I minus j alpha is a square. You never bothered verifying that, and if you did get to the end of the computation and try taking a square root and suddenly realize, whoops, that element isn't a square, then, wow, okay, just add a few more characters and redo. You can do that really quickly reusing what you did before, so it's not a big deal. What's important here is that once you have enough characters, then the obstruction group goes away. The product of I minus jm and the product of I minus j alpha, those are both squares. Okay, so that is the algebraic part, and now I want to move on to the slight optimizations that you can do, and then try to tell you the final exponents, why we get this cube root of log n. You can, as in the case of the Q sieve or the quadratic sieve, which I've basically skipped, you can write down sublattices. You can write down, instead of looking at all pairs I and j with I and j up to some bound like y, you can look for the sublattice of i's and j's where q, well, there's several sublattices of i's and j's where q divides, say, the norm form of I and j, the norm of I minus j alpha times fd. If you pick one of these lattices for a big Q, and if the lattice is, as most lattices are, kind of squarish, so has two vectors both of similar sizes, then that lattice kind of expands I by a factor of square root of Q and expands j by a factor of square root of Q. If you see what that does to I minus jm times the norm of I minus j alpha, it expands it by square root of Q to the power d plus 1, d for the norm having dth powers in it, and plus 1 for the I minus jm having first powers in it. But then it divides it by Q, so it's maybe not expanding by as much as you would expect. If you look for any particular limit on how big these numbers are, how big the congruences are that you want to have being smooth, for any particular Q, how many sublattice elements, how many pairs I, J in a particular lattice, forcing Q to divide J to the D F of I over J. These lattices, by the way, being easy to find. If you look for a particular bound, how many I's and J's there are, well, it's something proportional to Q to the minus D minus 1 over D plus 1. For instance, if D were 5, that's Q to the minus 4 over 6. Q to the minus 2/3. There's some drop-off as Q gets bigger in how many congruences there are up to any particular limit. But certainly the integral of Q to the minus 2/3 being something that grows with the range of Q, it's certainly a good idea to use lots of Q's. All right, in this case, you can't take huge Q's. It's not like the Q sieve or the quadratic sieve where you can take the special Q's, these sublattices, to be as big as you want. You really have to look at small values of Q because, again, there is some drop-off in the number of congruences below any particular limit as Q grows. But if you take Q's between, say, 1 and y squared, then just integrating, you see there's about Q to the 4 over D plus 1, for instance, Q to the 2/3 again, times as many congruences if you look at a bunch of sublattices compared to just using the Q equals 1 sublattice. That's a lot more congruences up to any particular limit. If you want to very carefully figure out, all right, how far should you go with sublattices, then you, as in the case of the Q sieve, you should look, when I say the Q sieve, unfortunately, I should have chosen a different letter for the special Q here. For the rational number field sieve, we were separately looking at the smoothness chances of I and n plus I. And you should do the same thing here, and then with a lot of detail, you figure out, okay, roughly how big should your sublattices be. The upshot is the same as in the case of the rational number field sieve, that the sizes of the congruences that you get are a little bit smaller than you would otherwise. Not so much to affect that L to the 1.9 exponent. A bigger improvement, which does come into that 1.9, is using multiple number fields. Instead of just using I minus jm times I minus j alpha, you can use also, say, I minus jm times I minus j beta, as long as alpha and beta have the same m. What do I mean by that? Well, instead of just using f, you can use, say, f plus x minus m. Let's assume that the polynomial f you started with, like x squared minus 14, and x squared minus 14 plus x minus 25, that those are both irreducible. Then calling beta a root of x squared minus 14 plus x minus 25, or generally f plus x minus m, you now have beta related to m in the same way that alpha is related to m. Well, beta, if you plug it into that f plus x minus m, it's a root of f plus x minus m, you get a map to z mod n from an appropriate integer ring inside q adjoining beta, as you did for alpha. So, writing down the second polynomial f, you now have twice as many congruences to play with, twice as many chances of smoothness. This requires you to do more work in linear algebra. Your exponent vectors have to be longer to account for having both q adjoin alpha and q adjoin beta. You have to make sure that you have squares in both of those fields, but you can limit that effect by just chopping down the number of primes you use for q adjoin alpha and q adjoin beta. It's still beneficial to have twice as many congruences to look at. You can save time handling both alpha and beta by merging the smoothness tests. You can look at I minus jm and I minus j alpha and say, what did it mean for that to be smooth? Well, we're first insisting that I minus jm be smooth. And that first test is shared by alpha and beta. If I minus jm is not smooth, you don't have to look at alpha or at beta. Only a small fraction of the pairs I and j have I minus jm being smooth. So you can just look at that small fraction of pairs, look at both alpha and beta for the occasional pairs ij where I minus jm is smooth. That'll take less time than looking at alpha and beta separately. You can go beyond f plus x minus m. You could use, say, f plus 2 times x minus m, keep going to a bunch more number fields. And again, this is important to get the best known asymptotics for the number fields. So I think that brings me to those asymptotics. The number field sieve, as I said, instead of getting e to the square root of log performance, has e to the cube root of log performance. So I'm going to be using a lot L, which is e to the cube root of log n, 2/3 power of log n, all the exponent. The time for the number field sieve, the number of bit operations in the number field sieve, not worrying about how much memory we need, the number of bit operations in the number field sieve is L to the 1.90 something, plus to the low of 1. Again, that's some degree 6 algebraic integer, not integer, some degree 6 algebraic number, but I don't care what it is, I just care about the real number value. It's 1.90 something. You will often see people talking about a much, much, much slower version of the number field sieve in the literature. Without using multiple number fields, people will often talk about the number field sieve taking a whopping L to the 1.92 plus a little o of 1, which is slower by a factor of L to the 0.02, which goes to infinity. It's gigantic. So I don't know, if you want the best parameters, you have to use multiple number fields instead of dramatically slowing yourself down to L to the 1.92. So okay, how do you get this L to the 1.90? Let me just do this properly. There's a degree d that you choose which grows with n, but slowly. The right asymptotics for it, d should be about 1.4 times the cube root of log n divided by the cube root of log n. So that's the degree. It should grow slowly as n grows. You don't want to have m being tiny, m being about n to the 1 over d. You don't want to have that being tiny, but it should not be as big as n. This is where the number field sieve gains over all the other methods, is that it writes down numbers that it wants to have being smooth, numbers like m or I minus jm, kind of like m. Those numbers are considerably smaller than n. And those numbers, since m is something like n to the 1 over d, well, let me just choose m now. M is some integer close to n to the 1 over d. Once you've chosen m, you're going to see that all the numbers desired to be smooth are only about log n to the 2/3 bits long instead of some constant fraction of log n. They're a lot smaller asymptotically. Having chosen m, you can write n in base m as m to the d plus f d minus 1, m to the d minus 1, plus etc. There's the polynomial f, where f of m is 0 modulo n. I've said here each fk is below n to the 1 plus epsilon over d, which is more of a range than you need. You could insist that f be as small as m. I mean, you could say each f sub d minus 1. You could specify m equals the floor of n to the 1 over d, and then each f is just write n in base m in the unique way where each f is between 0 and m minus 1. But then you might run into trouble. For instance, that f might conceivably maybe be reducible. So in order to make an algorithm that works conjecturally for every n, we'll allow some randomness. We'll allow the f's to be maybe a bit bigger. If some f doesn't work for some reason, then just drop another one. In practice, when people are factoring RSA numbers, well, every f that you write down works. It's awfully hard to find one that doesn't, but in theory, if you want an algorithm that conjecturally works for every n, then just vary f a little bit. If you find yourself in trouble, try another f. Okay, the prime bound, y, is the 0.95 power of l. The congruences, the y squared congruences that you write down are all the I minus jm's and then I minus j alphas, where I and j range up to about y being L to the 0.95. So y is a little bit smaller than L. Let me emphasize that y is something like square root as many digits as m. If you look at log y, which is like log L, that's what? It's about the cube root of log m. Versus m, how many digits are in m? What's log m? Well, that's about the 2/3 power of log m. And that's what you expect, that the numbers you want to have being smooth, these I plus j m's, are just a little bit bigger than m, for I and j being pretty small, as they are here. The hoped to be smooth numbers should have something like square as many digits as the smoothness bound. And that is what's going on. Y, again, L, Y, all on the same scale. Those are about cube root of log n digits. And M, I minus jm, those are about 2/3 power of log n digits, which is about square as many digits. That's what you expect for good smoothness bounds. Anyway, having chosen the y is about L to the 0.95, you have to do L to the 1.90 bit operations to look at all those pairs, I comma j, and then for each one you do L to the epsilon time with the elliptic curve method or sieving to figure out which of the I minus j's are smooth, and that reduces the L to the 1.9 smooth pairs ij down to just L to the 1.65 under reasonable conjectures about smoothness probabilities. You use actually a fairly serious number of number fields to get the best known exponents. Use L to the 0.12 number field. If you want to know what all of these numbers are, figure out those algebraic integers that I claim the exponents are, the limiting exponents, you could just figure out, all right, what are all the relations between these numbers, like this number plus that number has to equal that, and then smoothest probabilities u to the minus u say that this number times that number has to equal that, and then you solve the equations, you'll see what the 0.12 is as a root of some polynomial, but okay. Use some noticeable number of number fields. For each ij, you look at all, for each ij where I minus j in the smooth, you look at all of the I minus j alpha, I minus j beta, continuing for L to the 0.12 algebraic numbers there, roots of polynomials like f and f plus x minus m, f plus 2, x minus m, and so on. And hope that you're going to get something smooth. Hope you're going to get a smooth congruence. I should emphasize at this point that the L to the 0.12 number fields times the L to the 1.65 smooth I minus jm's, that's a total of what? L to the 1.77? I've written in the middle. L to the 1.77. That's not a bottleneck in the algorithm. Later we're going to do just a little bit more with that spare time. But okay, continuing the number field sieve, after this negligible part of the computation to find the smooth I minus j alphas, I minus j betas, to find smooth congruences, well, if you look at how big the I minus j alphas are, measured by the norm, measured by j to the d f of I over j, then you see it all on the same scale as m. When m is n to the 1 over d, it's about log n to the 2/3 bits. And if you look at y and I and j, which are all about log n to the 1/3 bits, and take the d power of those, you end up at the same scale of log n to the 2/3 bits. I've written down a precise exponent here that the norms we want to have being smooth are about the 2.86 power of m at most. Most of them are on that maximum end. If you then plug that into reasonable smoothness conjectures, and you get about the desired number, about y smooth congruences out of this whole process. You get L to the 0.95 smooth congruences. Compared to the exponent vectors, which have, for every prime up through y, they have one rational component, that's L to the 0.95. And then for each number field, L to the 0.12 number fields, something I didn't emphasize yet is that for the Q join alpha and Q join beta and so on, you use primes only up to L to the 0.82, which times the L to the 0.12, if you fill in the dot, dot, dots, gives you the same L to the 0.95. All right, so if you make y big enough within the L to the 0.95 plus little of 1, there will be more smooth congruences than exponent vectors. You will get a square, which conjecturally always succeeds in factoring, well, of small number of squares. Each one has a 50% chance of factoring. To repeat what I said about how big these numbers are and where that 1/3 comes from, why it's cube root of log n. Again, there's several different sizes of numbers. There's n itself, has about log n bits. There's smaller than that is m. M is only n to the 1 over d, so it's about log n over d. That's about log n to the 2/3 bits. And then much smaller than that, there's L and Y and I and J. Those are about log n to the 1/3 bits. All of these are balanced when you realize the nth powers between them. You have to have this cube root of log n when you try to simultaneously have y being what it normally is for smoothness. Have smoothness probabilities make sense for numbers on the scale of m being y smooth. That tells you that y, log y, the number of digits in y squared, should be about log m. You also want to have the norms, the j to the d f of I over j, in other words, norm of I minus j alpha, those should be about the same size as m. And that means that y to the d should be about as big as m. And also, you need m to the d to be about n just by construction of the polynomials. So looking at those three approximations, if log y squared is log m, and d log y, well, y, the d is about m, so d log y is about log m, that says d has to be about log y. And then d times log m, that's log y times log y squared, is about log n. Log y has to be about cube root of log n. Paying attention to the log factors gives a more precise log n to the 1/3, log n to the 2/3. All right, I have a few minutes left, and I have a couple of slides. To repeat what I said at the beginning, the number field sieve is better than anything we know how to do with the small primes techniques. The elliptic curve method factors n in time e to the square root of log n log n. The elliptic curve method takes time e to the 1.9 cube root of log n squared with log n, which for sufficiently large n is small. The elliptic curve method is much better for finding small primes, but the number field sieve is the method of choice for finding sufficiently large primes of big numbers. I've copied the latest number field sieve record, which was finding a couple of primes, each about 332 bits long, which is a lot longer than, well, you certainly don't want to guess 332-bit prime numbers. You don't want to do row. Even doing the elliptic curve method would take a very long time. The computation used only about 5 times 10 to the 18 opteron cycles, which is about, what, 2 to the 60 cycles, machine cycles, which is a lot less than 2 to the 332. The number field sieve scales really well, and as the sizes of numbers you want to factor goes up, this was factoring a 664-bit number. If you think to factoring, say, 1024-bit numbers, it still sounds like a doable computation. Question?
Was it all done on opterons, or was it partly done on?
That's a good question. I would have to ask Finding about that. I remember that at least part of it was reported in opteron cycles, but I don't know what other machines they might have used.
Some like big memory computer for linear algebra stuff.
They might have, but always remember that the linear algebra is not a bottleneck. If it is a bottleneck, then you just reduce y, and it's no longer a bottleneck. So the machines chosen for that are less critical than the machines used for finding smooth congruences to begin with. But I don't recall enough details in the announcement to say whether there were more machines than just the opteron.
Dan, what's an opteron?
What's an opteron? It's a magical computational device that does computations that heretofore unheard of. So this is an AMD Athlon 64 with a little extra, well, it has a slightly different socket from the Athlon 64. It predates the Athlon 64. It's AMD's server-designed chip. But if you run the same computation on an Athlon 64 that you buy for a few $100s, then you will get the same number of cycles. All right, last slide for today, and the next time I'll get into the research questions of trying to really optimize a number field sieve instead of just crudely optimize it as I just did, instead of just figuring out to the 1 plus little of 1 power how fast it is. Next time I'll do really how fast it is. But let me finish today with a little more about the asymptotic exponents, namely batch factorization. We've seen this for finding small factors, sieving, remainder trees. Those find small factors of a lot of numbers in only polynomial time per number. A lot faster than even the elliptic curve method, which is not polynomial. It takes sub-exponential time per number. If you have a bunch of numbers to handle at the same time, and you want their small factors, then you can do that more quickly than handling the numbers separately. The same is true for the number field sieve. Remember that inside the number field sieve, we were looking at L to the 1.9 pairs I comma j, and only L to the 1.65 of them were used for the next stage, for looking at whether I minus j alpha and I minus j beta and so on were smooth. And then the number of number fields we used, the number of number fields we used didn't make up that difference. There was still lots of time between L to the 1.77 time for looking at n and seeing whether alpha and beta and so on had smooth I minus j alpha, I minus j beta. The time for that was much less than the time to look for smooth I minus jm's. One way to exploit this is to say, okay, we're going to look at, what is the ratio there? L to the 0.13. We're going to look, well, actually it's the same L to the 0.12. We're going to look at L to the 0.12 different numbers n, all sharing the same M.
If you have a bunch of n's, say 512-bit numbers, 768-bit numbers, and you just choose some plausible m, it's going to be a good m that you can use for all the numbers. Just write down different polynomials for each one with the same m. And then they can all share the same I minus jm smoothness test. And then you just have to do L to the 1.77 operations for each of the n's separately, which is still, if there are not too many n's, then that's not a bottleneck in the algorithm to finish finding squares for all of those n's. In the same L to the 1.9 bit operations, you end up finding squares not just for one number n, but for something like L to the 0.12 numbers n. In the cryptographic context, that might sound more threatening, that instead of just factoring one number in this time, we're factoring a whole bunch of users' RSA keys all at the same time. It's not quite that simple because, last paragraph here, if you look at the time for linear algebra, that goes up to by a factor of L to the 0.12, but then you can reduce y and you still end up with a savings. You still end up factoring a bunch of numbers more quickly with the number field sieve than factoring each one separately. I'll stop with that. Again, next time I'll be doing detailed optimization. Thank you for your attention.